Math is really the study of patterns, if you think about it, and a relation is really just that. It's a connection between two things that often involves a pattern. One thing is connected to another. So, definition of relation, a connection between two or more things. For our purposes, it'll be two things. And we can express relations in lots of different ways, which you've talked about in the past. We can have a table of information. So we could have one thing connected to another. It might be if you work for 1 hour, you get paid $10. 2 hours, you get paid $20. Okay, 3 hours is $30. There's an obvious pattern here. We could translate that table, that numerical information, over to a graph. The first column is our independent variable, which we plot horizontally. The second is our dependent variable, which we plot vertically. And in this case, we get a linear pattern. A third way to represent a relation is an arrow diagram, which is like a table. Each element in the first is connected to the second. A fourth way is using a set of ordered pairs. So our first coordinate, comma, our second, okay, which relate to the points on the graph. These are ordered pairs. The order matters. The first coordinate is related to the second. And we could put those inside of a set. Okay, so a set of ordered pairs. And a fifth way to express a relation sometimes is if there's a pattern between the first and the second that we can see, we can write an equation. So the x value, in order to get the y, if we multiplied x by 10, 10x would equal y. Now, there are different types of relations, as we're going to talk about, but one key concept is that of a function. And a function is a special relation in which each input value, which we're going to call domain, is matched up with only one output value, which we're going to call range. Let's look at these concepts through some examples. Alright, in my first example, I have a connection between the month of the year and the number of days in that month. So, first of all, is this relation that I've got shown here a function or not? And it is not a function, because each x value is not matched up once. You'll notice that February is matched to 28 days or 29 days, depending on whether it's a leap year. Alright, each of the other months is matched up once, but February is not. So it's not a function. Our domain is the set of all input values. So that would be January, Feb, March, April, May, and June. I've only gone the first 6 months of the year on this. And the range are the possible outputs. I can get 28, 29, 30, 31. So I simply list the output values in the range, the input values in the domain. Alright, here's another relation. Is it a function? Is each input value matched up once? The answer is, it is a function. Each input is matched up once. Now you might wonder about the 14. 7 matches to 14, 9 also matches to 14, but each input value is matched once. The fact that they're matched to the same y value doesn't matter. It's each input value x is matched up once. So this is a function. And the domain is, let's list the input values, 3, 5, 7, 9. The range is what gets outputted, 10, 12, and 14. Okay, next we're going to look at something called function notation. And to begin just with something you're familiar with, if I have an equation, a relation in equation form, I can translate that into a table or an arrow diagram. So for example, if my input was 0, 2 times 0 plus 1, my output is 1. If my input was 1, my output would be 3, and so on. Alright, so you're familiar with that typical notation. Now what I'm going to do here is I'm going to call this entire procedure, what's happening here, I'm going to call my relation, I'm going to give it a name. Now I'm going to call it F. It's not a very exciting name. Okay, but what's going on here is F. My input value is producing my output value in some predictable way. So another way of writing this equation is to say my machine, my function, takes each x value, so it takes 0 and it outputs 1. It takes 1 and it outputs 3. My machine F takes 2 and it outputs 5. This is my input x, this is my output y. So what we often do is we write this equation as f of x, which is how you say it. F of x is, how do I calculate this y? By going 2x plus 1. These statements are equivalent. It's just a different way to represent the relation, which in this case is a function because each input is producing one output. Alright, f, g, and h are common names for functions, and we can get into more interesting functions with time. But here's another function, g of x is 4x minus 3. So you can think of it like your machine g, your procedure g, is taking a number. So for example, from my input bubble, if I took 0 and I put 0 into the machine, 4 times 0 minus 3 would spit out negative 3. If I inputted 1, which is g of 1, means I'm putting in 1, what comes out? Well, 4 times 1 minus 3 comes out, which is 1. Okay? Input and output. Now you can start doing other things with function notation. So if I said, well, let's put in a, g of a. So that's like thinking of, in place of x, I'm going to put a. So if I put a here, what's going to come out? 4a minus 3. What if I put in a minus 3? So now I've got to think that this means to replace x with a minus 3. So 4, replacing my x with a minus 3 in brackets. And then I can simplify that expression to 4a minus 15. Finally, what if we were asked to find the value of x such that g of x is 10? Okay, so our machine is g, which is referring back to this equation. G of x is 4x minus 3. This is saying that I don't know my input, but I do know my output. So I know that 4 times something minus 3 must turn out to be 10. Okay, that's the meaning conveyed by this expression. So what's the value of x? If I add 3 on both sides and divide by 4, therefore x is 13 over 4. Alright, we have an equation here that relates the cost of providing a feast for n people by this equation. So just to get a sense of what's going on here, let's just do a table. And the variable that's isolated is usually the dependent variable, which is the second column. The other variable is the independent. And the way to think about this is that the cost of running the feast depends on this, on the number of people, not the other way around. So independent and dependent. If nobody shows up, according to this relation, 25 times 0 plus 100, it's going to cost $100 to have that feast prepared, even though there's nobody around to eat it. One person, 25 times 1 plus 100 is 125. And 2 times 25 plus 100, 150, and so on. I'll notice that for each one person increase, I have a $25 increase in price. So you get the sense that the cost of this feast is basically $25 per person after the beginning $100, which is to get the hall rented and just some basics that are fixed costs. Now all that's being asked for here is to write this relation in function notation. So function notation is of the form f of x, something to that extent. The easiest way to do this one would be to say the cost as a function of the variable to follow, n, c of n, is equal to 25n plus 100. Okay, if we have a feast that costs $3,000, the question is how many people attended. So that's saying on our cost function, okay, and remember by function we mean each input has one output. Okay, for a given number of people, there's only one cost. There's one associated cost for a given number of people, so it's a function. So if n people show up, the output is going to be 3,000. How many people is this? Well, we could simply equate the 3,000 to this to calculate what n must be. And if you divide 2,900 by 25, you get 116. So therefore, 116 people attending costs $3,000.